Since we will be talking a lot about dynamical systems, it's actually not a bad idea to try and define what they are, right? So one way of looking at a dynamical system is saying that it consists of two different ingredients. On the one hand, you have a collection of possible states that the system can be in. And on the other hand, you have some sort of update rule that tells you how you move from one state to the next state. So if you have some sort of black box update rule and you input the previous state into this update rule, what this update rule will tell you is how the system will evolve to the next state. Okay, so that's a dynamical system. A system that moves between some set of states governed by an update rule. Let's look at a very simple example of this. Say you're a biologist and you want to study how some sort of bacteria multiply as you culture them in a petri dish. So you have a petri dish that you put in an incubator, and once every hour you take out the petri dish and you count the number of bacteria that you have. And then you put in your petri dish at the start of your experiment with just a single bacteria. If you take it out 1 hour later, it turns out you have 2 bacteria. And if you repeat that procedure an hour still later, you have 4. And then every hour, it basically doubles the number of bacteria that you have. So for this particular system, very simple exercise, just pause and write down the update rule for this system. So the update rule tells us what the state at time step n is as a function of the previous state, and let's call that xn minus 1. So x is the size of the population. In this case, that's part of the family of integer numbers. And n is basically the time step here. So every hour we do an experiment. So this is a discrete time system. Now, since we double the population every hour, this means that xn is just 2 times xn minus 1, right? So this is not rocket science. Okay. So very simple example of a dynamical system. Now, there's very different types of dynamical systems. On one hand, you can distinguish them based on whether or not they are deterministic or stochastic. So if you have a deterministic system, then everything is basically known in the system based on their equations. So what we had up here is indeed a deterministic system because nothing is left to chance. If we do have some chance, some stochasticity in the system, then you have a different type of system. For example, systems with noise, they're not deterministic, they're stochastic. Now in this chapter, we will only focus on deterministic systems. There's already quite a lot of fun, interesting things we can say about this. But bear in mind that, of course, in real life, we will also have noise in the mix. And therefore, stochastic dynamical systems are also very interesting. So that's one possible dichotomy between types of dynamical systems. Another distinction you can make is whether or not you have a discrete time system or a continuous time system. So discrete time versus continuous time. In the experiment we described earlier, where you take out a petri dish just once every hour, that's a discrete time system. And that discrete time system is governed by a difference equation, like the equation that we had up here. So just for discrete time steps. Now, of course, you can also take a different look at the same process, and that's saying, okay, it's not because I don't look at my petri dish that the population doesn't evolve. If you then take a different approach of modeling time as a continuous variable, then you end up with a continuous time system. And in this case, for this infinitely small time period, you're no longer governed by difference equations, but by differential equations. Okay, so this lays the groundwork for some of the things we will be doing later in this chapter.